two.
All right, hi everyone. This is Ryan, and welcome to another episode of Training Data. Today we got a really exciting one lined up. In the booth with me today, I have Nick Weir, data scientist with Cosmic.
Hi everyone.
For those of you who don't know Nick, some may argue that he's the MVP this year. He's been thrown about 100, or at least batting.
I don't know about that.
Batting 1,000. Don't be shy, Nick. And if you haven't really been following his work and some of the blog posts on the downlink, he's been writing a lot about our results from our most recent SpaceNet challenge, SpaceNet 4 specifically. And honestly, I've really enjoyed reading it, not so much enjoyed editing it. But it's kind of struck me like the Terminator series. Each one got better, except there was no Terminator Salvation. It ended on a good note. I really appreciate that. So today what we're really going to get into is not just the results from SpaceNet 4, but the motivation for why we as a group were interested in Off-Nadir data and kind of what that means for the future of computer vision and geospatial processing. For those of you who kind of haven't followed along in the past, SpaceNet is a nonprofit LLC that includes Cosmic Works, which is an InQtel lab, Digital Globe, Radiant Solutions, AWS, and Intel Corp. To date, we've hosted 4 competitions, and you can find all the information, not only about the Dataset competitions and code, on SpaceNet.ai. So just to jump right in, Nick, why don't you walk us through a little bit about what SpaceNet 4 was, and then what was our motivation for it?
Yeah, absolutely. So our previous 3 SpaceNet competitions were all based on imagery that was taken more or less straight down on the location that was being imaged. And those were building detection and road network extraction challenges, where we were asking competitors to identify these features in images taken looking very close to straight down, very similar to what you'd see on Google Earth or something like this. But the problem is that that's not always representative of the type of imagery that you're dealing with in the real world, particularly in urgent situations where you need to collect new imagery and analyze it rapidly. A great example of this is disaster response, such as after Hurricane Maria, when the humanitarian OpenStreetMaps team mounted this major remapping effort to map all of the roads and all the buildings in the territory of Puerto Rico for aid distribution by FEMA. They relabeled all of the roads and all of the buildings in the entire territory. This was over 3,000 kilometers of more than 30,000 kilometers of roads and 950,000 buildings. They did this all manually, and it took a long time. And part of the problem there is that the imagery that you get immediately after a natural disaster or something like this, you don't have time to wait for a satellite to be directly overhead. And so it's often taken at a substantial angle. And this could be very challenging to algorithms that are supposed to identify building footprints or extract road networks or things like this. But we really didn't know because we hadn't explored this in any of our previous challenges. And so what we set out to do was determine whether or not algorithms are able to identify buildings in imagery taken off-nadir at an angle. And if so, how well does it perform compared to normal, quote-unquote, normal directly straight down nadir imagery at that task, and what are the challenges that make it hard?
Because then in theory, right, if you can use more imagery off the satellite, whether it be off-nadir or right overhead, it dramatically increases the utility of the asset, right?
Yeah, absolutely. That's definitely the other major factor that we need to consider, is that if you want to get good coverage of the Earth from a satellite or a small constellation of satellites, you're going to have to deal with having the satellite turn and look at an angle at a lot of these locations.
Yeah, and this is really particularly timely because I know this was a concept that we were at least talking about when we first started Cosmic almost 4 years ago, and it's something that has come up more and more. I know just in the Wall Street Journal over this weekend, actually, they had a whole article on commercialization of space and all the different services that could be provided. And one of the things that always kind of struck me about this is I love the excitement, and I love all the focus that the domain's been getting, both in the startup realm as well as in the media. But there's really no quantification of performance. And we're kind of getting to the point where we can start to maybe not answer those questions definitively, but we can start putting some numbers behind it.
Yeah, we can definitely start setting a benchmark for how well can algorithms work on off-nadir imagery compared to nadir imagery. How well can they work if they're looking south and the sun is coming from the north and it's getting reflection straight into the satellite versus the other direction where it's dealing with a lot of shadows? How much does it matter if an algorithm was trained on the same look as the imagery that you're trying to analyze?
It's also kind of cool, and maybe it's a tangential effect to this, but I'm imagining this would also influence how different companies that are maintaining constellations would think about collecting imagery.
Yeah, definitely. I mean, if a company is unable to perform analysis with imagery that's taken very off-nadir, then it's going to be much less valuable. The collection companies are going to be much less likely to collect that and downlink it. And as they build out new constellations of satellites for imagery, it's going to constrain what types of collections they want to do, and that will, to some degree, control how they set up their constellations. And so if we can understand what the limits are of utility for different types of collections, then we can help companies define how they're going to set up their future collection platforms.
Yeah, that's cool. I'm assuming this was a really novel data set, right? It was something I know that the fact that we couldn't find anything when we first started talking about this problem all those years ago tells me that there probably wasn't a lot out there. And just even getting any type of real collect that's off-nadir, that's in a meaningful way, is probably in and of itself challenging. So,
yeah, absolutely. I mean, we know of two different sets of collections like the one that we used in this data set, and ours is the only one that's been open sourced, making it feasible for other people to work with. And of course, we often struggle with finding well-labeled data sets in order to develop machine learning algorithms, particularly in the geospatial realm. So this collection or set of collections is really special because it came from a single pass of a Digital Globe Worldview 2 satellite over Atlanta. So all of the images in the data set were taken within 5 minutes of one another, and this really helps by limiting changes in lighting, changes in placement of objects or structures on the ground that may take place over the course of time, and any other variability. And so we're really able to focus on how changing look angle influences algorithmic performance. And so during this single pass of the satellite, it took 27 images over Atlanta. And there were 665 square kilometers of overlapping geography covered in all of these collects. So all of these collects covered that same area. And these collections ranged from 7 degrees off nadir all the way out to about 54 degrees off nadir, which is very substantial. Buildings get really distorted. You can often deal with a lot of shadows. And you also get a substantial decrease in resolution. Those images were about a third the resolution of the most nadir images. And just as a point of reference, the first collection over San Juan, Puerto Rico after Hurricane Maria was just over 50 degrees off nadir as well. So this is a good reference point for what some urgent collection data looks like.
And this, you would say this is a really unique collect for Worldview 2, right?
Yeah,
this isn't
absolutely.
something they're doing a lot.
Yeah, this is one of only 2 such collections that they've done at Digital Globe with any of their Worldview satellites. It's a very special data set.
Cool. Well, so with every SpaceNet data set, right, there's the imagery, and then there are the labels that we assign within that imagery. So what did we do in this case?
Right. So for this data set, we worked with Radiant Solutions, one of our partners, and they did expert labeling of all of the building footprints in the imagery. So this was about 127,000 building footprints that they labeled. And it's important to note that they labeled these in a geographically accurate manner. So they're labeling where the actual building is on the ground, and therefore the labels don't change as you go to different look angles. And so this is really important if you want to try to build models that can learn geographically accurate placement of objects from very off-nadir images where there's going to be some distortion and things won't necessarily be geographically accurate. So Radiant Solutions went through and did all of this labeling, and we ended up with this very complete set of labels that covers all of the buildings that are over 20 square meters in this 665 square kilometer area.
Did it also include roads? Because I know we've had on past pods, we've had Adam come in and talk about roads work. Roads, same issues that buildings would have from being included or in shadow, or particularly if it's in a first responder initiative. Arguably, sometimes roads are more important to find first than buildings.
Yeah, absolutely. So the roads are also labeled in this data set. Yes, we did not use them in the challenge that we're going to be talking about today, but the roads data set is out there.
So I feel like I should have asked this just because I'm curious. Do we know how many roads are named Peach Street in Atlanta? I feel like we probably should have had that as a sub-label. Was that covered?
Probably
in the
should have. It would have probably been pretty challenging for the algorithms to learn, though. Maybe that'll be SpaceNet 15.
Yeah. It's like every other street, isn't it? I was driving around Atlanta, and Atlanta's a cool town. I was looking for the aquarium because it has a whale shark, and like every other street. I was like, how does anyone learn this place? It's confusing.
That's what Uber's for.
All right. So SpaceNet, you heard it here first. SpaceNet 15. Coming to you in 2020, street identification in Atlanta. All right. So anywho, so we done. All right. All right. So now we got the data set. How do we go and structure the competition, right? Because I know when we were first talking about this internally, it's one thing to have this awesome set of imagery. It's another to have the labels on top of it. But performing a benchmark right is a non-trivial task. And there's a lot of different ways we could have broken out the imagery to evaluate it. So how did we decide it?
Yeah, so when we split up data sets for running competitions, there are a couple of key factors that we think about. One, we want to do the best that we can to make each different data set distributed the same way geographically, and in this case, distributed the same way in terms of which look angles are contained within the data set. So we randomly selected small tiles from within this 665 square kilometer area and placed them into each of these three groups, which I'm going to talk about in a minute here. And so, and then included all of the look angles from those geographies within one given subset. And so when we split these things for competitions, we create a training set, and that's the data set that includes about 60% of the imagery, and that includes not only the imagery, but also we give the competitors the building footprint labels along with that. And that's the set that they're using to try to build an algorithm that can identify building footprints. We also give them an unlabeled test set. So that's the imagery, no building footprint labels. That covers about 20% of the total ground area. And that's the set that the competitors use to test themselves during the course of the competition, and that we use for the public leaderboard as we run the competition.
And we, as an aside, we have all that broken out correctly on the AWS page, correct?
We do. We have both of those up on Amazon Web Services in the SpaceNet dataset repository, which you can get access information from on the SpaceNet website.
And so in theory, right, anyone could try to replicate the competition for themselves for their own purposes.
Absolutely. And we certainly encourage people to do so. And in fact, if you need a starting point to do so, the algorithms that the competitors built, as well as the baseline algorithm that I built before the competition, are all publicly available on GitHub.
And if someone beats the competitor and they submit it to you with the results, does that result in a free coffee with you?
I mean, yeah, if they want to travel to DC and come find me, I'd be more than happy to chat about it and hear how they solve the problem.
All right, be careful what you wish for.
Yeah.
All right, little motivation for all you out there. Get excited. All right, so you structured it well. But how do we break out all the images? This was the first time in any of our competitions, or really any of the work we've done in Cosmic in general, where we've had, outside of the Comet TS project that Jake's run, where we've had a stack of data, not just a single image. So how do you break that out and divide it for scoring purposes?
Sure. So, and it's really important to make sure that you do this the right way, because if it gets split the wrong way, when you're giving the competitors different pieces of the data, then you could get some leakage, which would result in issues in the competition. And I should mention there was one more split that I didn't get to earlier, which is the validation set that we hold back completely. And so we don't give the competitors the imagery or the labels, and that's the set that we use for the final testing in the competition. So our goal with this competition was to understand how look angle influences algorithms' ability to identify building footprints. So what we did was we split the look angles into 3 separate bins. The nadir set, which is everything under 25 degrees off nadir, or less than or equal to 25 degrees off nadir. The off-nadir set, which is between 26 and 40 degrees off nadir. And then the very off-nadir set, which is the stuff over 40 degrees off nadir, and that's the set that's very representative of a lot of urgent collections in natural disasters and things like that. And so we asked competitors to identify the building footprints in every different one of those look angles independently in a set of specific geographies. And then we asked them to give us those predictions, and we scored them in 3 separate sets. So we scored them in the nadir bin, the off-nadir bin, and the very off-nadir bin, and then averaged those 3 scores. And the scoring was using the same SpaceNet metric that we've used in the past for building footprint competitions. And you can read more about this on our blog, but it's an intersection over union metric followed by an F1 score.
And not to jump ahead to the results, but based on how we bucketed out the data, would you recommend doing it, or do you think we did it right, or do you think there was maybe some changes that need to be made based on just even how you bracket, or even how you define off-nadir versus very off-nadir?
I think we hit it pretty well, and I'll get to this more when we get into the results more. But we learned a lot about how performance changes as you go from your standard Google Earth-esque nadir imagery to the off-nadir stuff and the very off-nadir stuff, and where the limits are there in terms of algorithms being able to achieve tasks like this.
Awesome. Well, on that, we're going to take a quick break and we'll come back and start talking about the results. All right. So you can, we just do this for our fake little commercial breaks we do.
Okay.
Okay. Cosmic's going to be back on the road in the month of June. We got 2 conferences. First, some call it the Super Bowl of the geospatial world. We just refer to it as the GeoWint Symposium. It's going to be in lovely San Antonio this year. It's going to be running from June 2nd to the 5th. We'll be covering the lightning talk session, talking about SpaceNet. Make sure to swing on by if you're going to be there. It promises to be an awesome event as always. And then later on in the month, we're going to be at the Computer Vision Pattern Recognition, or CVPR, also somewhat of a major event in our domain. That's going to be from June 16th to the 20th down in Long Beach. Specifically, we're going to be supporting the Earth Vision Workshop, which occurs right before the conference. So hope to see you out. All right, with that, back to the show. All right, and we're back here talking with Nick Weir about SpaceNet 4, and we're getting into the most exciting part, which is the results. This is something that I read in the blog post once and then started reading it again and just couldn't stop. That's probably the same for everyone. It's not just for me. So with that, without further ado, so Nick, let's talk about the conclusions, right? Because this was something that was exciting because we had some ideas about what the results would be, but we didn't really know. There was nothing really to point to. This was really, as we were saying earlier, it's a novel data set, novel competition. So walk us just through some of the high-level results first, and then we can kind of dig into some of the specifics.
Yeah, absolutely. So at a general level, the algorithms performed very, very well on the nadir imagery. This was the highest score that we've ever seen for any SpaceNet competition, and this is really exciting, and it shows that algorithms are continuing to get better and better. We saw an F1 score of about 0.85 at the highest for the nadir imagery, or 0.82 to 0.85, and so that was fantastic. We saw a surprisingly small drop when we moved to the off-nadir bin. So this was with look angles between 26 and 40 degrees off-nadir. Competitors still identified building footprints in the about 0.75 range, 0.7 to 0.75. Which suggests that there's still a lot of utility in some of this off-nadir imagery for automated analysis. And so we're excited to be able to show that value. Performance started to degrade when we got beyond that. The F1 scores for building footprint extraction in the very off-nadir imagery, so images over 40 degrees off-nadir, was on the order of 0.6 or a little less than that. So this meant that the competitors were identifying something like 60% of the building footprints that were in the images with a false positive rate of about 1 in 3.
All right, so what I'm hearing you say is, don't sleep on off-nadir imagery, but when it comes to very off-nadir, not good enough, huh?
At the current state of the art, it's probably not going to be good enough to take the algorithm's output and use it directly or with minimal quality control. Whereas with the most nadir imagery and the off-nadir imagery up to 40 degrees off-nadir, it's pretty good. There'd be relatively minimal human cleanup needed in order to use the labels that come out of these algorithms. And that's exciting. I mean, it would be able to help us do things like reduce the amount of time it took to create a foundational map after a natural disaster if we could get an algorithm's output as the first pass and then have human labelers correct it instead of having to draw the whole thing from scratch.
So what's killing very off-nadir performance, right? Because honestly, I thought that even in just that off-nadir bend, so anything before 40 degrees, I actually thought there'd be a more precipitous performance decline, but there wasn't. So what killed very off-nadir?
Sure, and this is something that is a little easier with some visuals, so I definitely recommend you check out the blog post that I've done about this competition where I highlight some of these specific challenges. But
for quick aside, for your blog post, if you read it, do you have to hand clap it 10 times, or is one time enough?
I mean, I appreciate all the claps that people want to give to our blog posts.
Yeah, I mean, just to be open here with everyone, I've hand clapped multiple times.
Yeah.
At first, I didn't know I was even doing it. So, all right. Anyways, I interrupted you. Please proceed.
So the challenges were things like shadows. So half of the collections in this data set were facing north. Half of them were facing south, or roughly half and half. These images were taken at about 11 a.m., so the sun was coming from the south and facing north. And so the images taken facing north, you get a lot more sunlight reflection off of things like the roofs of buildings. Whereas the images that are taken facing south, you're not getting that same reflection. And there are a lot of shadows cast by things like the buildings on the side of the building. And that makes it really hard to see the buildings even by eye in some of these images. And so that posed one major challenge. And we did, in fact, see in some of the off-nadir imagery, we saw worse performance from the competitors' algorithms in the south-facing images than the north-facing images. Another big challenge, or something we thought would be a big challenge, was the resolution decline. So resolution goes from about 0.5 meters per pixel in the most nadir imagery to over 1.5 meters per pixel. And we expected that this would have an effect on algorithm performance, but it really didn't. And this is something that you can see we examined very directly in a recent research study that we did on this data set, which is available on Archive, where we normalized all of the imagery to the lowest resolution in the data set and tested to see how well algorithms could identify buildings. And this ended up having more or less no effect on performance.
And on that note, for all of you listening to this pod, if you look in the description, we have links to that Archive paper as well if you're interested in learning more and getting into the details.
Sure. Yeah. And then another thing we were curious about the effect of before we ran this challenge was how occlusion of buildings would influence the algorithm's performance. So particularly in downtown Atlanta, where there are a lot of very tall skyscrapers, we wondered how having these things essentially blocking other buildings was going to influence the algorithm's performance. And that certainly turned out to be a factor. If you can't see a building because it's behind another building, then you can't predict that a footprint's there. And another big thing related to that is how the distortion of these buildings was going to influence the algorithm's ability to correctly place the footprint that it produces. So if an algorithm is learning to find the roof of a building, and a tall building's roof is going to be very offset because you're dealing with very off-nadir imagery, then this is going to be a challenge. And several of the competitors did, in fact, building correction for this, where they shifted all the building footprints in one direction or another.
And was it, because honestly, I thought this is where there was going to be a ton of problems. Mm-hmm. Just because even if it can do a decent detection, making sure it's in the right location is a non-trivial task. Was it just a matter of just building in some preset shift on the off angle of the imagery, or is there something more to it than that?
That was certainly part of it. And I mean, there was also we also saw some exciting results where algorithms were able to learn to correct for some of this offset on their own.
That's what I'd be looking for.
An algorithm could essentially understand what the look angle was that the image had been taken at, and as a result could correct the building footprints differently in different images. And so that was really exciting and not something that you see too much in your standard natural scene photographs, the normal pictures of cats and dogs. You're not dealing with this kind of correction of the geometry based on changing looks. So this was something really cool that we got to explore in this data set.
One of the other things that really struck me about Atlanta and just looking at the imagery, and I've come to just love and hate looking at that imagery, as you know better than I. I
love it. It's beautiful.
All right, you ride with Atlanta. Got it. The one thing that really surprised me was how forested some of the suburban areas were, and we knew that was going to be a problem. How did that turn out? I mean, that's the same thing as a shadow occlusion, right? If you can't see the building, right, you can only make a guess. But one thing I know that we were debating early on was, does a partial occlusion have the same effect on performance as a major occlusion? So essentially, is there, like everything else, is there some threshold that algorithms can perform against?
It's a great question, and it's something that should be explored a little more in the future. All we can say at this point is that, yes, if you have a building particularly in suburbs where they're densely packed, you have tons of trees overhanging buildings and things like this, even in the most nadir looks, algorithms don't perform as well at identifying those building footprints. There was about a 0.1 drop in score, so that's something like a 15 to 20% drop in score, depending upon where you are in that range.
That's significant.
Which is certain, it's very significant, and that tells us something about what types of geographies are going to be really hard for algorithms to learn in. And there's also interesting questions about how you should deal with labeling features like this. Should you still label the whole building even if part of it's occluded, or should you draw the outline around the occluded fraction of the structure? And that depends a lot on what you need, what your use case is, and whether you really need to be able to label the whole structure, or you only want to know what part you can see.
That's an interesting point. In general, just imagine a general foundation mapping application.
Mm-hmm.
Based on all the experience that you have, as serving as a challenge manager for this, you get deeper into the code and the data than anybody. What would you recommend? I know it's application dependent based on what you just said, but I feel like from what we put together, the occluded tag was still the right approach. I'm just curious in looking in the rearview mirror on this one.
Absolutely, yeah. So for those who are listening, the way we did this was we drew the outlines or Radiant Solutions drew the outlines for the building footprints only around the portion of the building that you could see in the nadir imagery. So they did not include portions that were occluded by trees in those nadir looks. And then they added a tag to the label indicating that the building was occluded. I think that's a good approach for most mapping applications, particularly if you're then trying to train an algorithm to identify these features, because otherwise algorithms are going to really struggle to learn when a tree is occluding part of a building versus when a tree is just a tree. And so I think this probably simplified things in the case that we were using, but again, it depends on the use case and what you need.
I'm assuming it goes without saying that if this was in a more arid climate, so one of the SpaceNet cities is Las Vegas. Let's imagine if we get the exact same data set. I'm assuming performance would just be a lot better, right? Because you have less trees, thus you have less shadows, you have less occlusions, houses are more spread out. I mean, it's kind of the story we've learned from all the other things where depending on the geography you're looking at, performance is going to vary. I'm assuming that's consistent here.
Yeah, that's definitely my expectation as well. I mean, the regions where algorithms performed the worst were these incredibly dense suburban areas. They worked quite well in the industrial areas. They, on average, worked worse on these small buildings. And so that's a combination of how difficult the suburban areas were, and just the fact that the smaller a building is, the less information the algorithm has to learn where a building is. And if it has a lot of information because it's a huge building, then it's going to make it much easier to identify.
Another thought here is, whether you're new to geo or not, any of you out there who have followed sort of the computer vision or just even more generally the machine learning domain in the last couple of years, you know that one of the things that people really look for in a model is generalizability. And really what that means is, in our circumstances, can it be applied to a lot of different geographies? So you can have the same model that can be applied to like a city like Atlanta, vice another SpaceNet city like Paris, right? So you're not having to retrain, burn up a lot of computational time, and essentially you can get a ton of value out of a single model.
And then you don't have to label new geographies anytime you want to train a new model, which is very expensive and incredibly time consuming.
Exactly. I guess my thought on this is, as it relates to that, particularly that very off-nadir bend, it seems like given how unique those data are, that we're still kind of far away from even thinking about a sort of a generalizable model in that case.
Yeah, absolutely. And this was something that we explored in the research article that I mentioned earlier that's on Archive, where we trained algorithms on specific subsets of the different look angles and then tested to see how well they performed on other look angles. And the ones that we trained on, all of them performed markedly better than, say, an algorithm we trained on nadir imagery and then asked to identify buildings in the off-nadir and very off-nadir bins. And this is really important to think about as you're trying to build algorithms that you're going to use in a deployment context, is if it's going to see new looks of an area, particularly new looks at a different angle or from a different direction, then it's going to make it very hard.
Got it. Right. Well, most pivotal time here. the Cliff Notes version. All right, what's the key takeaways here, Nick?
I'd say the key takeaways are that we're still a couple steps away from being able to build algorithms that can identify buildings with high fidelity in very off-nadir imagery. That said, we've gotten to a point where predictions are quite good in nadir imagery and in anything really under about 40 degrees off nadir. At least at the score threshold that we set for this competition. And that's another aspect that I explored in one of the blog posts, where we looked at how if we increase the threshold for how much of a building you had to get right, how would that influence performance? And when you go above this 0.5 threshold that we use, performance does go down pretty significantly. So at this threshold, some of these algorithms are approaching deployability in terms of performance. The amount of time it takes to train them and then to run them, it's a whole nother issue. Some of these were quite slow. They would take over a minute per square kilometer to perform inference, and that's too slow to use in most deployment contexts.
I think, though, you're hitting on an important thing, which we've talked about a little bit at Cosmic, but we certainly haven't done anything to date, which is actually trying to do a real test with disaster data. I think that could be something that could be really valuable to the whole response community, and something we should look at more. And now that we have a lot of not only these repositories, but a lot of the analysis that you've done and others have done, I feel like we're in a position to maybe do that in the future.
Yeah, I absolutely agree. I mean, our whole kind of guiding principles for all these SpaceNet challenges has been to walk before you try to run, and to try to achieve some of the earlier tasks and show that they're possible before we move on to something more challenging like disaster response or damage identification or change detection. But as this challenge has shown, we're starting to approach the point where you can take nadir imagery and get pretty good building footprint extraction. And so future challenges can explore things like trying to classify the buildings in the data set, which is directly related to things like disaster response, trying to classify the amount of damage in different areas to identify where response is needed.
Well, Nick, this has been awesome. I know this was a competition that a lot of people looked at and followed, and so thanks for all the work you did on it. And that we're going to give you a little bit of a break as we move into 5, and we'll be having an upcoming pod talking about this. But for SpaceNet 5, challenge manager on that is Adam Van Etten, Cosmic's technical director. He led the SpaceNet 3 effort, which was focused on road network and routing. We're back with roads again. This time we're going to be focused on yet another element, which is not only the network routing, but also timing. So keep your eyes peeled for not only future blog posts, but upcoming pods on that.
Yeah, he has some really exciting ideas for that challenge. I'm really looking forward to it.
All right. Well, Nick, this was a lot of fun.
Thanks, Ryan.
All right. Take care, guys.